So in this video we're going to be looking at the performance tasks that are available for you to use during Unit 3 of Math 3, our polynomial functions unit. There are altogether 4 polynomial tasks that are available for you to use during this unit. Of those 4, task 3 is the one that is absolutely essential. It is the one that you will see on the unit assessment. And so I'm going to begin by looking at that task. Before we get into that though, I want to point out to you, this is the unit pacing guide, a quick overview and more details right here day by day. And you will already laid out for those polynomial tasks. You don't have to worry about somehow squeezing them into the unit. They're already set in this unit. And so the first one we're going to look at is polynomial task 3 as the most important task. Although it is scheduled for day 10, you're very flexible. You only need to be through day 3 to be able to have the kids have all they need to access this task. And so depending upon special schedules, block days, and things like that, you can use this task anytime after that point. I'm just going to show you why the tasks are placed where they are. There's about 3 new things, then a task, 3 new things, then a task, 1 more new thing, and then a couple tasks as we get ready for the test. So 7 new things, topics altogether, and 4 tasks. So the first one was set on day 4 because, let's see if I can zoom this in a little bit so you can see better. Or maybe I can't, so let's just zoom down here. There we go. It can be done after day 3. It includes an optional extension about odd functions. Maybe just an honors class would want to do that part. On day 8, there are really nice things to discuss about day 7's homework. And so day 8, it's not to have to give a lecture also. After you've spent all that time talking about homework, to just move into a task, which doesn't require any lecture, but you can just get going on that. On day 10, also day 9, or worksheet 7, our last topic of the unit, had some very nice things to be able to discuss, and so you might want to spend more time talking about that homework afterwards. There's some cool patterns that emerge as the students do homework, and you might want to talk about that, prove that is true, and then we schedule a task here. Again, that way there's no notes. This is the task that we scheduled, was the one that appears on the unit assessment. And then day 11, it's when you're going to begin your review, so it might be a nice day to do a short polynomial task, or a long if you do the graphing calculator utility part task, and then have review for the end of the period and homework. So with that kind of overview of the unit, let's look at the task 3, the key task of the unit. So task 3, but when you download this, you'll actually see a title typed on there. That's this is still in edit here. But task 3 is about a curve of best fit that has been fit to temperatures over a month in the year 2011. So these are the low temperatures every day in January for 2011, and they're not the actual low temperatures. They're convenient low temperatures that could be true if we're talking Celsius. And so what you'll see here is this is dates. So this would be the 1st of January, this would be the 4th of January, the 6th, the 10th, the 21st, the 21st, 25th, and the 31st of January. If we were just plotting the data, they would be discrete points. For those of you who teach Math 1, discrete and continuous were 2 words they learned in Math 1, and so they would be discrete separate points. Because we're talking about a function that models the behavior of the points, the function that we would write would be continuous. And so we're doing a graph of a model, and so because of that we have a continuous function. Nice conversation if somebody would bring that up. That's why that's connected. And so the first thing is just to make sense, a little sense making. We see this graph, we've learned all these words. Here's some key words: domain, range, intervals where functions that increase and decrease, x-intercepts, things like that. And we would like them to think of that in context of temperatures in Fresno. And so we just asked them to make 3 observations that could be written in a newspaper article about this data thinking about x-intercepts, thinking about increasing and decreasing. So there's lots of different things they might come up with. We're just trying to get them to translate from a math context to a real world context. So 3 that I wrote were the daily low temperature was 0 degrees or lower from January 4th through January 25th. And you'll see here's the temperatures, here's 0 degrees right on the x-axis, and from the 4th all the way to the 25th we're at 0 degrees or lower. The second thing I chose to put was the daily low temperature ranged from a minimum of -4 degrees Celsius on January 21st, right here, to a maximum of 10 degrees Celsius on January 31st. And the third thing that I chose to write about was the daily low temperature increased from January 6th to January 10th, right there, and again from January 21st to January 31st. So they might also say something about when it decreased, when there were relative minimums in the temperature or maximums, this one relative maximum in the temperature. So lots of things. Just apply the math words that they've used to this real life situation and make it make sense. That's the point of that one. There's not a test question like this. It's very difficult to grade. There's so many different things. The next part says now we're looking at, the next part says now we're looking at February, a map of February, model of February, and there's 3 different proposed models for this graph. This is related now to the material they specifically covered in 3.1 through 3.3. And each of these models is incorrect, and they're supposed to say why they might be incorrect. I find on most of them there's multiple reasons they might be incorrect, so they just need to come up with one of those. This is a great discussion point where they can defend their reasoning and critique the reasoning of others. And so you might have students quietly write and then discuss as a class. You might have groups talk about this and then share out in groups. So here was what I came up with for these 3. Model 1, somebody proposed this model. I looked at this, I said, well, this is a quadratic function, and this graph definitely does not look like a quadratic function. They did tell us that a is a constant greater than 0, so I would expect it to start high and end high, but a quadratic function is just a normal parabola, and this is not. So that's what I wrote for model 1. For model 2, I looked at this, and there's a lot of things you might think are wrong. One thing is that this would come out to a cubic function, which if a is positive would start low and end high, and that doesn't do that. That would be a good answer. The one I chose to write was about the x-intercepts. If I solved for x-intercepts, setting y equal to 0, I would get -3, -9, and -20. But in fact, on our graph, the x-intercepts are +3, +9, and +20. Someone might also comment that this is wrong because of the bouncing and crossing that we see. We should be bouncing at 20, which would imply an even exponent on this factor, and that's not there. So model 3, I looked at this one, and it's a 5th degree function. It's an odd function, so I might say, well, this graph doesn't represent an odd function because it starts high and ends high. I might have said lots of other things, but I decided to focus on the bouncing and crossing this time. And so since these are even multiplicity, even powers, I would expect the graph to bounce off the x-axis at these points, so come down and then bounce back up here, and also at 9. And I would expect it to cross at 20 because this is an odd multiplicity, and this graph does the exact opposite of that. So those were different things you might see your students write. Then it asks for a better model. So the model that I came up with here was y equals a, x minus 3, x minus 9, and x minus 20 squared. And so this is really a nice place to pick up your weaker students. If you've talked as a class what's wrong with all of those, you've really given them a lot of hints of how they can write this function. So I would like to see kids try to explain to the class and have people agree or disagree, and then everyone on their own try to come up with a model, because I think after all of this discussion you should have even weaker students come up with a correct model. They're supposed to then justify their better model, so there should be some writing. So what I said, an a had to be positive in mine. This model is an even function that crosses the x-axis at 3 and 9, odd multiplicity, and bounces off the x-axis at 20. And so that's why how I justified my function. So this is a nice place to catch people up who've been a little behind. And then the last piece of this task gives an April graph. And the April graph has this pattern. They said compare it to the February graph. So I would want to have the 2 pages separate for myself so I can project them next to each other. So here was February. Actually, here was February, and here was April. And I'm going to do it this order because this is the order that they happened. This was the original graph, and they are going to ask us to explain the relationship between the graph for February and the graph for April, and use that relationship to create an equation for the temperature. So I would encourage my class to not speak and look for anything they saw in common between these 2 graphs, because students need a little bit of time just to let their eyes go back and forth and try to distinguish what is happening here. And so try to keep the spoilers from spoiling that for people. Eventually, I would hope, or I might hint along, like, what do you notice about the x values on these points? Because if they hadn't noticed that before, this one has 3 as the x value, and this one has 3. There's 9 and 9, 20 and 20. And the y values on these points are all 0, and then in April, the y values were all 12. This sort of suggests to me a vertical shift of up 12. The only thing is the graphs aren't the exact same shape. As a matter of fact, they appear to be mirror images of each other. So I also think that it might be that this graph has been reflected over the x-axis before it was shifted up. So that's the curve that I came up with. This graph was reflected across the x-axis and shifted up 12. And to write the equation for that, I wrote negative f of x plus 12, where f of x is the temperature in February. Or you could use the model that we came up with during part C and go negative that model plus 12. You might be tempted to give your students the practice of multiplying all this out. I want to encourage you that if you were going to do that, they should have a number here for A. And you could even say, let A be 2 or something like that. But doing that is just the pure practice of multiplying that. Here is where we have a good view of what's happening in terms of shifts and reflections in this form. And so this form is really the most illuminating in terms of seeing what's happening to the function. So that's what's going on with task 3, and that's a task that every class should do. I want to remind you this standard that we've been working on quite a bit over the last 3 things. Identify the effects of the graph by replacing f by f of x by f of x plus k, etc., etc. At the very, very end of this standard, they've tacked in include recognizing even and odd functions from their graphs and algebraic expressions for them. This is a key standard. We definitely want to be able to know this. This is not so much a key standard. It is another standard that we're supposed to teach. It's not quite as relevant to every single problem as the generalized shifts are. But task 1 in this unit gives us a chance to look at even and odd functions. It's really the only chance that we have all year for this to come up. So it would be nice to do task 1 because it's not the most important standard that we have. I also wanted it to be an opportunity for some creativity. This would be one where I think it would be nice to work with a partner or a group on this. It does say do the work on a separate paper, and you'll find as you try to do the work on the paper, here's me trying to fit this work on this paper, you end up getting something that's not so legible. So I would definitely have the kids do this on a separate paper. Just for a quick overview right now, I'm going to show you my lovely work here. Again, not what I really want from the kids. You're going to want to do this pre-problem work. Try to have the kids create a second-degree polynomial that has an x squared term and a constant term. No x term. I don't think that's really explicit there, so they shouldn't have a middle term. They should just have a squared term and a constant term. X squared plus 3, x squared minus 5, something like that. And it has integer zeros. And they should, with their partner or with their group, be able to come up with, if you have a difference of 2 squares, you're going to get 2 integer zeros. If I can factor this, then I should be able to get 2 factors that give me integer zeros. Now if it's x squared minus 5, these would be square root of 5. Those would not be integer zeros. And if there's a plus, there's no factoring in that, and we won't get integer zeros. So they should come up with that this has to be a difference of 2 squares. Now the real task is to make a 4th degree polynomial function that meets these criteria. the leading coefficient, let me zoom that in again, and the zoom does definitely not seem to be working on my camera, so I'll just get closer. We want a fourth degree function that meets that the leading coefficient is positive. There are 4 distinct zeros, so I should be able to factor it to 4 parentheses, all of which are integers. And the polynomial has no x to the third or x term. And this is a task that you might have them play with for a while. I would, as a teacher, make up one that doesn't work. Make up maybe an x squared plus 3 times an x plus 2 times an x minus 1 or something, and multiply that out and have them see that you're going to get some x to the thirds or x's. So they need to find a way to not have any, or just make 4 separate factors, x minus 1, x plus 2, x plus 3, x plus 4, multiply that out and see that they're getting some x cubes and x's. Because from that, then they should explore in groups, and this was a big hint. What really will work for them, and if you need to, you can start, is there any way we could use difference of 2 squares to get a 4th degree? That would be a good hint as they work along. Because if you multiply 2 difference of 2 squares together, first of all, when you factor it, you'll get 4 separate linear factors that will lead to 4 integer zeros. And when you multiply it, you'll get an x to the 4th, but you won't get any x to the thirds. You'll get an x squared term, and you'll get a constant term. And so that's what you're going for. This is kind of frustrating / fun. You really need to work through what kind of hints and helps you can give them. You don't want to drag them there before giving them the joy of discovering. And so really work on how can you bring them along without just telling. Once they get a polynomial that is made from the difference of 2 squares, then they're supposed to verify it meets the conditions. So one way is they could factor and solve for the zeros to show there's 4 of them. They could multiply it out to show that it has a positive lead coefficient and no x cubed or x terms. And they could graph it to show those 4 distinct zeros. When I graphed this, I got a y-intercept of 36. It's important for them to graph it, even if they feel like they've done it already, because when it asks about the line of symmetry the next time, looking at a graph will help them see that that symmetry is happening right here. And what we're wanting them to discover in the next few problems is that everything that happens over here also happens over here. There is a positive 3, 0, there is a negative 3, 0. There's a positive 2, 0, there's a negative 2, 0. There's probably some point over here that's 1 comma something, and there's negative 1 comma that exact same thing. Looks like that was 24 in my case. And because each student made different functions here, they might not all get the same answers when they do a table. If somebody has x squared minus 1, x squared minus 3, I'm sorry, x squared minus 9, that will be a little different. But what should happen is as they plug in 1 and negative 1, they should get the same answer. 2 and negative 2, they should get the same answer. And they should see the symmetry of the situation, that the y-axis ends up being the line of symmetry. And that's called an even function. Here it's defined algebraically. And they're asking kind of what does that mean algebraically? When it says prove algebraically, what they want you to do is find f of negative x, put negative x into your function that you made. So I put negative x to the 4th minus 13 negative x squared plus 36. When I took these to the 4th or to the 2nd power, they became positive. So it came out to the same function I had started with. That's an even function when that happens. That's the definition of an even function. And then it says, explain why all even functions have the y-axis as a line of symmetry. So they want you to really understand what this is saying, that f of 3 and f of negative 3 will be the same value. F of 7 and f of negative 7 will be the same value. And that is visually, graphically symmetry across the y-axis. From there, that's the end of this task. If you have an ambitious group that you didn't have to drag through getting a function, then the extension is a nice explanation about odd. You could talk through, without making them do it, you could talk through, why do you think these are called even? And most kids that I talked through this with said, well, because there's even exponents. They feel that evenness is getting rid of the negative. That's not the whole definition of even. The whole definition is this, and it ends up applying to trig that has no exponents. But that's what that's what they'll say. And then, so they guess that odd functions will have odd exponents. Again, that's not the whole definition of an odd function, but it's a good guess from where they're at. And I think you could have this conversation without even assigning them the rest. It turns out, if you want them to do that, if you have them make equations that categorize as odd, they'll pick things with odd exponents. Like I said, these are not the only kind of odd functions, but that's what they will be hypothesizing. I think it's a good hypothesis. And when they plug into these functions, it says they're going to have 4 separate tables here for these 4 functions they made on their lined paper. So here I did for h of x. When I plug in 1 and -1, I don't get the same answer this time. I got opposite answers. When I plug in 2 and -2, I get 8 and -8. When I plug in 3 and -3, I get 27 and -27. And so what happens is you get opposite answers when you plug in opposite numbers. Graphically, it looks like this, and it asks them, is there any symmetry? And in fact, there is something called point symmetry in odd functions of symmetry, but point symmetry is if you turn something exactly 180 degrees upside down, it looks exactly the same. So here I find this looks to be in the first quadrant and the third quadrant. When I turn it over, it still looks to be in the first quadrant and the third quadrant, still going through the point 0, 0 upside down and right side up. So that's an odd function. The actual definition of an odd function is this, that f of -x is the opposite of f of x. That's the actual definition of an odd function. And again, this is all an extension piece that you may or may not take the time to do. You could just do it rapidly with a graphing calculator. Well, give me one you think is odd. Let's type it in and see what it looks like. But this is like I said, our only chance to talk about even and odd during our curriculum, and it was a standard. So that is task 1. Task 2, I'm just going to show you the answers page. There is a worksheet and then there's typed answers. So task 2 looks like a modeling problem. We wouldn't really call it a modeling problem because students aren't making this model themselves, but it does help them make sense of what a model is. And so in this one, they give them a model that has been made. I don't think the kids are going to have any understanding of where this came from or how that could possibly work, because this isn't really a problem where they have modeled anything. But now we're just going to practice understanding how that works. And so it goes through and asks them several questions that would be related to the work they've done in the chapter. It's a 3rd degree polynomial function. Evaluate it for 1. They get -4, and then they have to interpret, and interpreting is the main thing about this problem. This isn't a really long all-day kind of problem. It would be nice to fall on a block as a short second thing. And so originally this was Branham's Burger Barn. I have since changed it to Bella's Burger Barn because I didn't need to have my name and everything. But they lost money. Notice we got -4, and negative is lost, but I put 4,000, and that's because P is in thousands of dollars. So when you get 4, that's 4,000. In the year 2001, we plugged in 1, not 2001, but T is the number of years since 2000, and so that's 2001. So the reading is really, really careful in this. And then it asks them to plug in, find out the profit in 2030. So if you plug in 30, you get this. This would be in thousands of dollars. So really, if they were thinking that this was an accurate measure, that would be $52,080,000. But this model, is it appropriate to use this model and make this prediction? No, this model is only good from 2000 to 2014, and that's a very common feature of models, that they work for a limited period of time, not for the entire -infinity to infinity of years. And so since we used this model past the time that it was made for, we can't really count on this being an accurate predictor. Then we have back to what we've been doing this chapter, determine when the profit was 0. So we want P to be 0. So if we put in 0 here and factor, we get 0, 2, and -1. Which of these answers is not in the domain? So again, we're thinking about the meaning here. Well, -1 would be 1 before 2000, and this model was only good from 2000 to 2014, so -1. And then it wants you to do a graph from 0 to 14. So I knew it was an odd function, so start low and end high. This would be my -1. There is 0, and there is 2, my zeros. and I drew a starts low and ends high kind of graph. But from 0 to 14 would only be this piece of it. And so looking at this graph, I would say it starts out, the Bella's Burger Barn starts out losing money, but after year 2, it begins to make more and more money every year. And so then they ask, for what year was the profit greater than 500,000? And so a good way for them to experience this is just by plugging in numbers. I did not do 0, 1, and 2. We already know 0 and 2 have 0 profit, and 1 you figured out in part B was -4. So I started at 3 and I plugged in all those numbers. And since profit is in thousands of dollars, we just want P to be bigger than 500, and then that will be 500,000. That happens first at year 7 and ever after that. And I'm pretty certain that even though I've only plugged in integer values, that there won't be any time where it goes back down, because I know what a cubic function looks like, and this should just increase after this. So the profit is greater than 500,000 for years 2007 to 2014. And they're not asking us to find what fractional spot in the year where it hit 500,000, like 6.2 years or something like that. That's not what they're asking us. They're asking us which years were greater than 500,000. And so 7 was the first year where we were over. All right, so that is task 2. Task 3 was the main one that we looked at. Task 4 is an optional one. It might be a good one to save at review time, but it does, what task 4 does for you is it practices quadratic formula again, it practices synthetic division again, and factoring with synthetic division. And so because of that, it is a nice task to review some of the topics in the unit. We will do a little bit more volume stuff in the second semester, so and geometric modeling, and so this volume piece wouldn't be bad as a review later in the year. But this first page all can be done without a calculator. It all can be done by hand. But this second page asks you to graph the equation and adjust the viewing window, and so this would be done on a graphing calculator or Desmos to be able to have the students graph and answer these questions. So this part, I would only do the second page if you wanted to break out the technology and you had access to that easily. So that is the 4th task. That's an optional task. What it does review for you from the unit is synthetic division, quadratic formula, and some things like that. So also another chance to make meaning of what would these words mean, what would this number mean in terms of this problem. All right, so I wish you the best of luck on all these tasks. Have a wonderful Unit 3.